And this is, again, part of how we helped deal with the issue of class full IP addressing. With our Class A networks, we had almost 17 million hosts. With our Class B networks, we had a little over 65,000 hosts. In our Class C networks, you jump all the way down to 254 hosts. So what would you do if you had a network of 2,000 hosts? What if you had 2,000 computers, right? 2,000 employees in your company. They each have a computer. What do? You're going to take a Class C? Well, it's not big enough. Well, you got to go to a Class B. If you took a Class B network, right? If you reserve this out on the internet, you're tying up 65,000 plus IP addresses. But you only have 2,000 hosts. So that means there's 63,000 IP addresses just sitting out there, unused. Boom, gone. That's a big old waste. So maybe your company says, well, I don't want to waste. So how about I go out there and I reserve for myself 8 Class C addresses, right? Because they take the 254 for each of those Class Cs, multiply 8 of those, you get a little over 2,000. Hey, I'm not wasting any addresses. But you have real cluttered routing table entries because out on the internet, it has to know that any one of these 8 different Class C ranges all go to this same company. It gets messy. That's when we used strictly classful IP addressing. Now we use something called Classless Interdomain Routing, or CIDR, which is sometimes referred to as CIDR, and I've also heard it as CIDR. Okay, I've always called it CIDR. I don't know what the correct pronunciation is. I suppose we could look it up. But I don't care what you call it. It's CIDR, Classless Interdomain Routing. And this uses a technology called Variable Length Subnet Masks, VLSM. This is why we had to learn the binary. See, the decimal subnet mask uses 255s and zeros. And if that's all we're going to use, well, we don't have a whole lot of choices, right? We got Class A, Class B, and Class C. But if we take that decimal subnet mask and we turn it into its binary equivalent, remember, it's all ones and then all zeros. But who says that we have to stop at one of the decimal points? Right? That's what the line is right now, right on one of the decimal points. Couldn't we just move the line either to the left or to the right and divide it? As long as it's between one of the digits, we're good, right? That's what variable length subnet masking is we don't have to use just 255 and 0. If we were to move that bar somewhere in the middle of one of those octets, we now end up with, let's say, 7 ones and a 0. Right? We moved it over just a notch. Well, that equals 254. Or if we moved over another notch, 252. Continuing on, 248, 240, 224, 192, 128. Or we're back down to 0, like we've had before. So if you've ever looked at an IP address and it's subnet mask, and you saw in that subnet mask something other than 255 or 0, I assure you, you saw one of these numbers listed here. A real common one is 252. Okay, there's a lot of internet service providers which will give a company just a couple of IP addresses based off of the subnet mask 255.255.255.252, which means the only portion of the IP address, which is host ID, is that very last 2 digits, which gives you, believe it or not, only 2 IP addresses. And that way, you're not tying up a whole bunch of IP addresses for some small company that only needs a couple, or maybe an individual at their house. So how does this all come together? Well, with the original subnet mask, we have all ones and all zeros divided right on the decimal point. So you have a network ID of 255.255.0.0 with a little over 65,000 IP addresses available. Or I could subnet that, but not the way we saw it before, where we break it all the way down to only 254 addresses with the Class C. But maybe I slide that bar right into the middle of that third octet, and we have the subnet ID, the portion that becomes part of the network ID. And you'll notice the host ID is now 11 binary digits long. Now, if you want to figure out how this works out, here's what happens. How many subnets do we then have available to us in this scenario, right? Because we've added, those 5 digits in the binary number to the network ID. So you do 2 to the n. I know we're back to exponential numbers, but 2 to the n or 2 to the fifth would end up with 32 possible subnets, 32 additional possible networks within that single B class network. And the number of hosts that are available, well, now we have 11 zeros to make up the host ID. So you get 2 to the 11th, but then you have to say minus 2. And the reason it's always minus 2 is because you can't have all zeros, you can't have all ones. If you do the math, 2 to the 11th is 2048, minus 2 is 2046 available hosts within each subnet. So in that scenario where you have the 2000 hosts, you could now go to an internet service provider who, using CIDR, I know I said I call it CIDR, but actually I call it CIDR. Other people I know call it CIDR. You can use CIDR and variable length subnet masks, and then the ISP could say, here's your pool of 2046 addresses, and that internet service provider could still hold on to the rest of the other 63,000 whatever to give to other companies who need them. Now, if we go back to our simple network, this will look just like what you've seen before, but actually I've made a slight change. The client's IP address and the server's IP address, and even the router's IP address, have all stayed the same. But you'll notice the subnet mask has changed. It's no longer 255.255.255.0. The last octet I've now changed to a 248. I will tell you that the problem here is that this network doesn't work. With that subnet mask, 101, 201, and 200, they can't all talk. Now, how do I figure this out and how do I know this?